Audio Jungle. Audio Jungle. Audio Jungle.
Greetings, engineers. Today, we're going to talk about the traffic impact assessment. Many people will be excited when they hear a new project, but some will be worried about one thing, the traffic congestions. These folks worry that the new project will attract the new trips and make the entire neighborhood congested. To find out, we will conduct a traffic impact assessment. Let me first define what is traffic impact assessment. Traffic impact assessment is a technical analysis of problems and safety issues relating to specific development. It is an important tool or study that identifies the needs for any improvements to a transportation system to reduce congestions, improve safety, provide adequate access, and mitigate the impact associated with the project. It, it also acts as a countermeasures for potential negative impact and responsible in predicting or addressing the potential transportation and traffic problems that will occur from the development. In short, TEA or the Traffic Impact Assessment is to investigate the impact of traffic generated from new development, also to identify the problem on the traffic due to impact, and to propose remedial measures to mitigate the impact. So here are the objectives. First is to identify whether a particular development project will have an impact on the safety and efficiency of adjacent roads. It means to assess how the project might affect the flow of traffic and the overall safety of the surroundings. Last is TEA or the Traffic Impact Assessment paves the way to investigate and develop traffic management plan that help minimize traffic congestions. The purpose of investigating and developing traffic management plan with the help of TEA is to minimize the negative effect of traffic congestions. These plans can include measures such as implementing traffic signals, optimizing routes layout, using alternative transportation option, or suggesting other strategies to elevate congestions, improve traffic flow, and enhance the overall safety and adjacent road. Why is traffic impact assessment important? The importance of TEA is to evaluate the ability of the surrounding, the proposed development in accommodating the increased traffic while still maintaining an acceptable level of service. Yes, it is a process that helps evaluate the potential impact of a developing project on the traffic condition. By conducting a TEA or the traffic impact assessment, expert can analyze how increased traffic volume or changes in the road infrastructure might impact congestion's level, the safety, the overall efficiency of the nearby road network. When is TEA mandatory for development projects? Cities will continuously expand urban and regional development projects ranging from malls, houses, schools, and commercial establishments. This expected growth remarkably impact the country's transportation system and the natural environment. TEA or the Traffic Impact Assessment important to conduct in order to first is to forecast additional traffic associated with a new development, determine the improvements that are necessary to accommodate the new development, assess in land use decision making, identify potential problems with the proposed development which may influence development decision, allow the community to assess impact of proposed development, help to ensure safe and reasonable traffic condition on streets after the development is complete, reduce the negative impact created by the developments by helping to ensure that the transportation network can accommodate the development. We conduct traffic impact assessment because we are concerned that the new development can cause congestions. Also, to conduct at TEA, we assess current condition and make estimate about the future condition. Thank you.
So why do we need traffic impact assessment? Traffic impact assessment will look at what possible outcome a specific action can have. Second, it is help it helps how to minimize or prevent the negative outcomes. Next are the benefits of traffic impact assessment. It provides information on the projected traffic expected from a proposed development and evaluates the impact of proposed development on the roadways in the immediate proximity of the proposed development. It also helps evaluate whether development is appropriate for a site and what type of transportation improvement may be necessary in order to maintain a satisfactory level of service. So this is the application for proposal development. From developer to consultant planner or architect or engineer, the local authority which is local government, then to planning department, to engineering department, and the technical department, the requirement for the DIAR, the traffic impact assessment. So documents required for the submission of the for one is current status of transportation. Second, development details, methods used to estimate traffic generation. Next is the traffic generation summary table, traffic distribution across the area, and assignment assumptions and associated traffic volume figures, traffic safety risk assessment, pedestrian and cyclist impact assessment, intersection assessment inputs, and a brief account of proposed construction work as part of the development. Thank you.
So we are going to proceed to the traffic impact assessment. So as you can see in the figure, it is the process flow in which someone can generate a traffic impact assessment. So first, as you can see in the figure, you can see that there are stationaries. So we have the first stationary is the developer, followed by the architect or town planner, then followed by the local authority, and so on. So now let's proceed to the traffic stream parameters. So there are three main variables or parameters for traffic analysis of highway performance. First is the flow, Q, or the Q vehicles per hour per lane, then followed by speed and density. Flow is defined as the number of vehicles that pass a one point on the roadway, sometimes per lane, during a specific time interval. So it is expressed in equation that Q is equals to N divided by T, in which Q is the traffic flow and vehicles per unit time. N is the number of vehicles passing some designated roadway point during time or T, and T duration of time interval. Moving on, speed is the average traffic speed is defined in two ways. The time spot mean speed, or the average speed of vehicles passing a point on a roadway over a specified time, or the instantaneous point speed. Example, radar gun, in which U is equals to the summation of W divided by N. So U is defined as the time mean speed in unit distance per unit time. U to the power of n is equal to the nth vehicle spot speed at designated point on highway, and n is equals to the number of measured vehicle spot speeds. Moving on to density, it is the number of vehicles occupying a given length of roadway at some specified time. It is the K is equals to N over L, in which K is expressed as the traffic density in vehicles per unit distance, sometimes per lane 2, and N is equals to the number of vehicles occupying some length of roadway at some specified time, and L is the length of roadway. Moving on, let's proceed to the variable relationship. It is a simple identity that provides the basic relationship between the traffic flow, the speed, and the density. It is the setting space mean speed as simply U for notational convenience. It is expressed in an equation that is Q is equals to U times K, in which Q is the flow or the typically in units of vehicle per hour, and U is the speed. Space means speed typically in units of miles per hour or kilometer per hour, and K is the density typically in units of vehicle per mile.
There are different basic traffic flow models, and I am going to discuss the first two, which is speed density model and flow density model. Let us discuss first the speed density model. So this model describes the correlation between the traffic density and the speed of the vehicle. So this relationship states that as the traffic density increases, the speed of the vehicle decreases, and vice versa. So let's say, for example, we have a congested roadway where the density is increasing. The speed of the vehicle there tends to decrease. It is because the vehicle there will experience more interaction and conflict with the other vehicles. The speed density model is depicted as a graph where the x-axis is the traffic density and the y-axis is the speed of the vehicle, since the speed of the vehicle is dependent to the traffic density. So as you can see, if the speed is at maximum, the density is 0. And if the density is at maximum, the speed is 0. So we have a formula, U is equal to U sub F, which is the free flow speed, times the quantity of 1 minus K, which is the density, over or divided by the K sub J, which is the jam density. So next is flow density model. This model describes the correlation between the traffic flow and the traffic density. So when you say traffic flow, it is the rate of the vehicles passing at a given point in a roadway. So as you can see, the flow density model is a parabolic graph where the x-axis is the traffic density and the y-axis is the traffic flow, since the traffic flow is dependent to the traffic density. As you can see, the graph in the model is parabolic. It is because initially the traffic flow increases with the density. But when the maximum point is reached, or known as capacity, the traffic flows start to decrease if the density further increase. It is because of the roadway congestion. It is the same idea with the speed density model or speed density relationship, but it is applicable when the maximum capacity is reached in the flow density model. So we have the formula for flow density relationship, which is Q is equal to U sub F, the free flow speed, times K, the density, minus U sub F over K sub J, which is the jam density, times density squared.
Good day. So my name is Michael Ipiang, and let's proceed to the one of the basic stream model, which is the speed flow model. So speed flow model also gives a parabolic function. It shows that two speeds are possible for flows Q up to highway capacity. Desirable for any given flow to keep average specimen speed on the upper portion of the speed flow curve. So it is desirable for any given flow to keep the average specimen speed on the upper portion of the speed flow curve. So when the speed drops below the U cap, so it means that the traffic is in a highly congested and stable condition. So the illustration below shows the visual representation of the interactions of all the flow, speed, and the density relationship. So we have here an example problem of the application of speed flow density relationships. Section of a highway is known to have a free flow speed of 55 miles per hour and a capacity of 3,300 vehicles per hour. In a given hour, 2,100 vehicles were counted at a specified point along this highway section. If the linear speed density relationship applies, what would you estimate the specimen speed of these 2,100 vehicles to be? So the first we have the jam density is first determined as K sub G is equals to 4 sub Q cap over U sub F, which give us a value of 240 vehicle per mile. And rearranging to solve for U. So we got the K sub G over U sub F times U squared minus K sub G times U plus Q is equals to 0. Those substituting the value, so we got 240 over 55 times U squared minus 240 U plus 2,100 is equals to 0, which gives you the value of 44.08 mile per hour or 10.92 miles per hour. And both of these speeds are feasible. So let's proceed to the models of traffic flow. Actually, there are two models of traffic flow, which are the Poisson model and the dimensions of queuing model, but let's focus more on in the Poisson model. So Poisson models is the models that account for the non-uniformity of flow are derived by assuming that the pattern of vehicle arrivals at a specified point correspond to some random process. The problem then becomes one of selecting a probability distribution that is a reasonable representation of observed traffic arrival pattern. An example of such distribution is the Poisson distribution, which expressed as P times quantity of n is equals to quantity of lambda times t to the power of n times e to the power of negative lambda t over the factorial of n, where p quantity of n is equals to probability of having in vehicles arrive in time, and lambda is average vehicle flow of arrival rate in vehicles per unit time, t is duration of time interval over which vehicles are counted, and e is base of the natural logarithm, which is the value of 2.718. So we have an example problem for vehicle arrivals as a Poisson process. An observer counts 360 vehicles per hour at a specified highway location, assuming that the arrival of vehicles at this highway location is Poisson distributed. Estimate the probabilities of having 0, 1, 2, 3, 4, and 5 or more vehicles arriving over a 20-second time interval. So solution, the average arrival rate lambda is 360 vehicle per hour or 0.1 vehicle per second. Using the equation with t is equal to 20 seconds, the probabilities of having exactly 0, 1, 2, 3, and 4 vehicles arrive are, which shows in the picture that we got p of 0 is equals to 0.135, p of 1 is 0.27, p of 2 is 0.271, P of 3 is 0.180 and P of 4 is equals to 0.090. So for 5 or more vehicles, we got the formula of P quantity N is greater than or equals to 5 equals 1 minus P, the quantity of N is less than to 5. Then put the values, we got 1 minus 0.135 minus 0.271 minus 0.271 minus 0.180 minus 0.90, and we got the final value of 0.53. So a histogram of these probabilities would look like this, which are the number of vehicles arriving in a 20th time interval, and this type of histogram is the probabilities in parentheses. So we have also limitations of the Poisson model. Empirical observations have shown that the assumption of Poisson-distributed traffic arrival is most realistic in lightly congested traffic condition. As traffic flows became heavily congested, or when traffic signal caused a cyclical traffic stream disturbances, other distributions of traffic flow became more appropriate. The primary limitation of Poisson model of vehicles arrival is the constraint imposed by the Poisson distribution that the mean of period observations equals the variance. So that would be all, and thank you.
Audio Jungle. Audio Jungle. Audio Jungle.